Okay, so we continue. Last time we introduced the Feynman rules and Feynman diagrams. Today we will continue describing more details about this Feynman diagram, Feynman rules. So let me just repeat what I wrote last time about the Feynman diagrams. Okay, the first rule is to represent a set of coordinates on which the sign psi dagger depend, and these coordinates are space, time, and spin indices. And you attach this set of coordinates to all these operators, and these are points in this space-time coordinate, and we will connect those points and form a solid line, a dashed line, or wavy line. Okay, so now we connect all these points representing this particle being created or destroyed, and that's space and time coordinate, and by a solid line which is directed from the creation operator on the right to the destruction operator psi on the left. Okay, so we already showed you some examples last time, so we will repeat that example today. And now we connect the arguments of this potential term, the points in the argument, by a wavy lines. So this wavy line represents the interaction. Okay, so the interaction connects these particles between these two points Z1 and Z2, where Z1 and Z2 represent these particles that are coupled to the interaction. For example, the Coulomb interaction. So let's just discuss the Fourier diagram that we discussed last time. So the first order terms that corresponds to the this Green's function in the interaction, in the presence of the interaction, g xy minus x2, are given by those four diagrams. This is the first diagram, second one, the third one, and the final one. So we should pay attention to this prefactor plus minus 1 in front of this diagram, because that is the signs that coming from this first order imperturbation, and we will come back to the sign in a moment. So the upper sign refers to the boson, and lower one for the fermions. Of course, there are other four terms which could be generated simply by interchange between Z1 and Z2, and also J1 and J2. So this is the this first order corrections to the Green's function in the presence of the interaction that we discussed last time. So today we will go on to describe more details for these diagrams. In particular, for fermion operators, if you can form a closed loop of fermion propagators or fermion solid lines, and remember there's which gives a factor -1 in front of this coefficient. So we will come back to this in just a moment. So for example, in diagram C here, so we have a fermion loop. So it's for these these two loops in diagram A. So but for diagram C, we have only a single fermion loop. Remember, this loop is formed by a creation-destruction operators that follows Feynman rules that you connect these points. Okay, so if these points that you connected to is actually going to direct you to the initial points, then this forms a closed loop. So for a single closed fermion loop that you can see from this Feynman diagrams, then you need to actually add the extra minus sign, -1, to this diagram. So we will come back to this just a moment. So this is the origin of this, one of the origin of this minus plus sign. In particular, this plus sign here, okay, for fermion. This plus comes from the double -1. So another -1 comes from when we do this Taylor expansion up to first order imperturbation. So we will come back to this in just a moment. Okay, so this is one remark. We should pay attention to this closed fermion loop, and this gives a factor of -1. And the second remark is that all internal variables, for example Z1, Z2, and so on, are to be integrated over, meaning we need to perform such a multiple integration over all the z variables. Remember, the z variables are the variables that connect these particles, and they are coupled by the interaction. Okay, so and we call them internal variables. So these internal variables are to be integrated over, and to see this, we need to go back to this perturbative expansion that we wrote down previously. That remember this S matrix or this unitary evolution operator. Upon Taylor expansion, you can actually expand this interaction, powers of this interaction V, right, or U, and as a result, we have to integrate over all this internal degrees of freedom associated with that time evolution operator. Remember that. So this S matrix, time ordered exponential, right? Okay, so when you Taylor expand this exponential operator, and of course there's a integration over the tau, and so that's how you get this the integration over this internal variables, the tau, but you also have the internal degrees of freedom to be integrated when those particles are attached to those d tau or tau prime. Okay, so and these are combined and are defined as z variables. So the z variables are the internal degrees of freedom that come directly from this expansion of this time-ordered exponential operator. And so we need to distinguish this external variables and internal variables. So this x are called external variables, which are not to be integrated over. So which looks like the original x variables, x1, x2, that are not to be integrated. And so, for example, this self-energy diagram, you could very easily see what I meant by internal and external variables. So this x1, x2 are the external lex or external variables that are the arguments of this Green's function itself, but everything else that are in between these external variables are internal variables. And these diagram is to modify the so-called self-energy of the original particle, and by modifying this Green's function. Okay, a single particle Green's function is to be modified by the interaction, and the interaction actually is just this red circle, which is kind of a wavy line connected to the solid line. But these two external legs represent the original creation, destruction of a single particle that you start with. So we will interpret this in just a moment. Okay, so this is to illustrate to you that you could easily classify the internal and external variables by drawing this Feynman diagram. So we need to integrate over all the internal degrees of freedom that labeled by z's, and we do not integrate over external variables. So the third remark is that the rules for constructing diagrams depend on the specific form of interaction. So I mentioned this briefly previously, that if we have a Coulomb-like interaction, and this is the interaction vortex that describes the Coulomb interaction, which is the interaction between pair of particles or pair of electrons, and you simultaneously destroy it and two particles, and you create another two particles, for example. Okay, so more standard, you destroy two particles at some point, and then later you create another two. Okay, so this is the typical two-particle interactions, say Coulomb, in the form of a Feynman diagram. So we have another very standard interaction, which is the electron-phonon-like coupling. We will come back to this in the future section, that we will discuss phonons and bosons and electron-phonon coupling. So this diagram represents the single electron interact with the phonon, which is a lattice vibration. So there's a electron come in, which get destroyed, and then later there's another electron created, but then you exchange the phonon momentum and energy when this particle, this electron interact with phonon. So basically, in this class, we most of the time discuss these two types of interaction. But of course, we have another type which is local interactions like delta potential. So you have a very sharp kind of impurity sitting somewhere in your sample, and then electrons, when they see this, say, Dirac-like delta function potential, then it gets scattered. So this is impurity, this disordered scattering. So we will discuss that too, right? So, and of course, there are other types of interactions, but then these three are the most fundamental diagrams for the interaction vortex. And let's take a short break. When we come back, and we will continue making some remarks regarding the Feynman diagrams. Is there any questions?
Okay. I want to ask a question. When you talk about the electron impurity interaction, why the impurity, the interaction not the long range, but everybody, many papers will mimic by delta?
Well, this is the. You mean why do we model this disorder by a Dirac delta potential? Okay, because there is some sort of, I should say, defect, right? So defect, meaning if we have a very standard periodic structure of your lattice atoms, then you don't have any extra scatterer. However, if you simply just remove an atom randomly from any sites, then of course, by removing that atom, you create a very large potential. Okay, so this is a kind of a periodic potential well that the atoms can actually sit, right? So if you just remove one of the atoms out of the system, and then you create a huge amount of potential. Because originally, this potential is to stabilize this atom sitting right there, but it's gone. So how can you model this kind of a very large and sharp potential disturbance? Well, Dirac delta potential is a very convenient way. Okay, so this is a very, very sharp perturbation, because you only remove this atom just right here, but not here, but not there. This is a very localized perturbation, and Dirac delta function is a very good approximation for that kind of disorder. It's called defect. And dislocation and other kind of topological defects that this could be imagined or constructed experimentally, by removing some atoms and then randomly, and this is the way that we model this potential. All right, of course, you don't need to use this Dirac delta function, but this is closest to reality that you can imagine, because this is a very huge amount of perturbation. So you need to flip this sign of this potential so that no atom can sit here, because this is very high potential barrier that all these atoms actually cannot sit here. Okay, so that's the idea. Okay, so let's take a short break. So I guess to get familiarized with all this Feynman diagram, Feynman rules, you really need to do exercise and homework, and then check the textbooks, references, all this kind of rules, and why do we have such a rules. There is a reason for that. Okay, so if there are no such rules, then you could actually create your own rules. You could construct your diagram attached to your name, okay, and then see if those rules agree with this, this perturbed expansion that we mentioned, and also if they agree with the Feynman's convention. Yeah, so once in your lifetime, you need to really trace back so these diagrams and their corresponding terms in the perturbed expansion. So you need to write down all this operator form of these diagrams and then really understand why is this a loop and where is the wavy line, why is there a wavy line, and why are they separated, and so on. Okay? But we will get to that later. Okay, so the final remark is that it is very clear that the number of diagrams you can form, you can draw, actually is exploding. Okay, because it's very simple interaction form, as we just saw previously, that there are 8 diagrams, right? And 4 plus 4. But you can imagine that if I keep doing this expansion to the second order, and how many terms or how many diagrams are there? Okay, I didn't know, so you can count. Okay, so maybe it's up to third order, you cannot control all this number of diagrams. You can imagine you cannot exhaust all diagrams for this particular higher order term. So very soon you have no control over the diagrams. Okay, even if the diagrams are already simplified to some extent, but still there are too many diagrams to be considered. Fortunately, there is a theorem called the Goldstone theorem or the link cluster theorem that I mentioned previously that saved our life, because we only need to consider the connected diagram, which are C and D in our previous diagram. Remember this, the first one, A, something like this, and B, this, and C, a balloon attached to the ground, and a self-energy like D. So A and B diagrams are disconnected because you could really separate these sub-diagrams by cutting a line through the whole diagram, so they are not connected. Okay, and so is this one. Okay, but if you simply just do the same thing for the C and D, you cannot do the job, because if you actually separate these two, you get meaningless diagram because they are connected already. So you cannot disconnect the diagram by simply just cutting this diagram from any angle. And so C and D are called connected diagram, and A and B are called disconnected diagram. So that's the power of Feynman diagram, because if you simply just write down all this operator form of these diagrams, then you would not know which diagrams are disconnected or which terms are connected. Okay, so right on the spot when you just draw these diagrams, you know very well that they are disconnected, so I can throw them away and I only need to consider C and D because they are connected. So, and the reason why these disconnected diagrams do not really count, because they get exactly cancelled in the Green's function by the denominator of this G. Remember that. Okay, there's a S of beta expression value respect to this unperturbed state, and then when you draw these diagrams are in the numerator, but they are exactly the same diagram in the denominator hidden in this S beta. So then these two contributions exactly cancelled. So the net contributions involve only the connected diagram. So this is called link cluster theorem, which we don't have time to prove, but I will mention this in more details later. Okay, so this is what saves this Feynman diagram and Feynman rules. So let me just sketch this Goldstone theorem or link cluster theorem. So it says that if you consider the nth order term in this G italic, remember those terms come from this perturbed expansion of this single particle Green's function in the presence of interactions. By expanding this time order exponential, when we do such expansion, there's a prefactor and also all this integration of a d tau 1 prime. Okay, so this is the nth order perturbation, and if we really want to calculate this up to nth order, and this is what we need to do. Okay, so you can imagine that there are n operators of H1, and each operator H1 contains many, say, operators side-by-side dagger, so you get n copies of H1. And you need to multiply this n copies of H1 with this side-by-side dagger, right? So how many operators are there? So there are so many operators. If n is actually 10, and this H1 maybe there are 4 or 6 operators, so 6 times 10, 60, plus 2, 62. 62 operators. How can you draw the Feynman diagrams of 62 operators that are multiplied together? This is almost impossible, but fortunately the connected diagram are sufficient. So, which means that the external legs plus all the interaction vertices are connected to each other, like this. A balloon with a string attached to the ground, and this is a typical connected diagram. And let me repeat what makes it disconnected. So for all those diagrams that fall into 2 or more disconnected pieces, which corresponds to a product of 2 or more expectation values. So remember, each pieces of this connected diagram is actually some expression value that could be evaluated separately. And if you have 2, you got a product of the 2 independent expression values. And link cluster theorem tells us that all this disconnected product of those expression values or disconnected diagrams will be cancelled out exactly by the new denominator of this Green's function when we expand this SO beta in the denominator. So there will be exactly the same type of diagrams that could be generated if you this disconnected diagrams appears both in the numerator and denominator. So this is numerator and also SO beta. So they get cancelled. And so this is why we don't worry about this disconnected diagram. And from now on, we don't even bother to draw this disconnected Feynman diagrams because they will be exactly cancelled by this SO beta in the denominator. So I don't have time to derive this or prove this, but I refer you to actually to read these corresponding sections in Feta Logica and also other references to prove this link cluster theorem. So the proof is actually very straightforward, meaning you simply just do the Taylor expansion for the denominator as you did for this numerator, right? And then you will see exactly that disconnected diagrams appeared. So that's the n up to nth order. So that's the idea. Okay, so let's take a short break. When we come back, let's just take this for granted, and then we start to build up our connected diagrams. We still have some sections that are yet to be discussed. So far we haven't done much real calculations, right? But we will do that in the coming weeks. For example, we will use what we know and learned about this Green's function and this perturbed expansion in Feynman diagrams to analyze this Anderson localization problem that we just discussed. And this calculation offers a very good, accurate description of what really happened when you actually put disorders on metals. Okay? So if you remove some atoms from these ordinary metals by rendering this kind of defects, and then you could create such a Dirac potential, and then we could discuss this simplest possible interaction in solid state, which is single particle potential, delta potential. But although this is not even simple, but the results are non-trivial. Okay, so depending on dimensionality, we may or may not have metal to insulated transition. So in short, if you consider a 3-dimensional metal and you actually disorder this 3-dimensional metal, and if the disorder effect is strong enough, meaning these defects concentrations are large enough, then you would destroy the metallity, the metallic behavior of this 3-dimensional metal. But if you do this on the nanowire or this metallic wire, then only a tiny disorder or this impurity concentration will destroy the whole thing. So this nanowire loses metallic feature as long as you just dope this by a tiny amount of impurity or create such a random delta potential. And this phenomena was first discussed by Anderson, okay, in 1950s. Okay? And all those experimental results, there are many examples which you could find in the literature that support Anderson's theory. And in 2 dimensions, this is so-called critical dimension. So this disorder effect goes like logarithmic divergence. So we will talk about this just right next to this definition. So let's just define this connected. So the total Green's function is just sum of all connected diagrams. This is the final message of today's lecture. So next time we will start from this statement that we only need to consider the summation of all possible connected diagrams. And this will do the job. And at this lowest order, it is durable because there are only a handful of diagrams that we can imagine, we can construct. So, and this is the thing that we will discuss next time. Even we can consider up to 2nd order, and in some cases 3rd order is also durable. Okay, so this greatly simplifies this calculation.